Hello everyone, welcome to the Soft Computing Practical series. Today we study about the backpropagation algorithm. So backpropagation is a supervised learning algorithm which is used to train multi-layer neural networks. Now this particular backpropagation, it helps the network to learn by adjusting the weights, and with this adjustment is based on the error between the predicted and the actual output. So in case of backpropagation, when we train this network, the network will make some predictions, and based on this, the output may not equal to the actual target. So how wrong it is, it measures that, and it corrects that by moving the weights in the right direction. Now in many non-linear problems like XOR, okay, so XOR is non-linearly separable. This function is it is not a linearly separable. So in that case we need multiple layers, and backpropagation helps such multi-layer networks to learn through the experience. And or they are linearly separable, but XOR is not linearly separable. For the purpose we need some more layers. Now there are two phases in backpropagation. There is a forward pass. In this, the inputs are passed to the network layer by layer to produce an output, and the output is compared with the whatever output we are getting, it is compared with the desired output, that is the target, and the error is calculated. Now in the second phase, that is the backward pass, the error is sent backwards through the network, and the weights are adjusted using the gradient of the error, that is using the calculus, that is we find the derivative, that is what say. Now the weights are updated based on whatever error calculation through the done through the calculus method. Now each weight is updated using this. The new weight is equal to the old weight plus the learning rate into the error gradient. And the learning rate, it controls how fast the network learns, and this error gradient tells in which direction and how much the weight should be changed. It is negative change or positive change, how much change it is. Now to understand backpropagation, we will first clear the concept of what is gradient descent, because this is the heart of backpropagation. So consider we have this a graph showing error on the y-axis and weight on the x-axis. Now this curve represents how error changes as we change the weight in our model. Now the bell-shaped or the U-shaped curve, this sometimes called as the error surface. Our goal is to reach the lowest point of this curve where the error is minimum. As you can see, this point at the bottom represents 0 or minimum error. The ideal weight where the network has learned perfectly. This is the point. So we can say that it is a bullseye where we are trying to hit. Now let's start for far away from that minimum, this particular point, okay, and calculate the slope. So this is the slope of this particular curve. Slope, or we call it as the gradient, or we can call it the derivative. Now if we calculate this, the graph, or sorry, the slope, this is very large slope. It means that we are far away from the actual value. As we can see, we are far away, so we have to take a bigger step to move towards the minimum. Now suppose we have another point which is closer to the minimum. Now as we move closer and we calculate the slope becomes smaller. It means the error is actually becoming less. Okay. So now if we calculate the slope, or we calculate derivative or the gradient, it is less. Now, and of course it is positive. It means we have to move closer to that particular point, okay, to the left side. Finally, when the gradient becomes 0 at this point, we reach the lowest point, the minimum error. So this is how the learning takes place in case of backpropagation. So if we calculate the slope is of course 0. So we have hit the bullseye. Now this is the neural network we will be considering in our case. So we have the input layer, we have the hidden layer, and we have the output layer. Okay, input is given to the input layer, then of course we have weights which are connected between the input and the hidden layer. It is not shown in this particular diagram, and hidden is also connected with the output with some weights. In our example, we will implement the XOR function. Okay, so for XOR function, 0 0 is 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0. So we must know this XOR function before implementing it. Now let us go for the practical implementation using Python. So before executing the Python code, let us understand this code. So here the first is we are importing numpy as np for performing mathematical operations. We use this numpy. Then this we are defining the sigmoid function to for the forward pass, and this is the activation function, and because of this we calculate the output. Then this is the sigmoid derivative. This is used in the backward pass where we calculate the error. Then here in this case we define the XOR input function. So we have two inputs. So there are four combinations: 0 0, 0 1, 1 0, and 1 1. Then the target output for the XOR function is 0 0 is 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0. So this is the output. Now after that we have this, we define a random seed so that we get a random value for initializing the weight. This is that. And then we define the input neurons, the layers, input layer neurons, hidden layer neurons, and output layer neurons. So there are two input layer neurons, two hidden layer neurons, and one output neuron. And this is we will initialize the weights and the bias. So this line initializes the hidden weights, this initializes the hidden bias, this initializes the output weights, and the output bias is initialized by the last line. Then we have the learning rate 0.5. This is used for calculating the we can say updating the weights. Okay, then we have the for epo in the range of 10,000. So how many iterations can be carried out? So this is giving. Then this part calculates the output of the hidden layer. So we give the input, and that input is given as the output to the hidden layer, and to calculate the output of hidden layer we use this formula. Then the output of hidden layer is given to the output layer. So this is how we calculate the predicted output. Okay, here we are using a sigmoid function, as we can see. Then this completes the forward propagation. Now next we have the backward propagation. So this part here we have the backward propagation. Okay, so this is where the error is calculated. Okay, so here, so in this case we first of all compute the error. So it is expected output minus the predicted output. Okay, and then we have to update the weight. For that updating we use the sigmoid derivative. How much calculation, how much updation should be done, that is what the gradient descent part. So this is what we are doing, the calculating that particular how much far away we are from the actual output and how much updating must be done. Now this part, it updates the weights and the biases. So output weight is updated using this, and output bias, then hidden weight and hidden bias. Then finally when we complete this, this lines, the first line it prints the final hidden weight, then the next line prints the final hidden bias, then the next line prints the final output weight and the final output bias, and here we get the predicted output. Okay, they must actually match the target output, so it must be close to 0 1 1 0. So let us see this, if we are getting this or not. We'll run this code on Colab. So now I am into the Colab. I have already copied the code. I'll just paste it. I'll just click here on the code, and here I'll just paste the code. So this is the code. Okay, you can see this is the code. This is our code. Now let us execute this. So after executing, now this is the output. So this is the final hidden weight, this is the final hidden weight. Okay, and then we have the final hidden bias, then output and output bias. Now this is what we are interested in, the final. So this is the first output. 0 0 is, of course this output is 0.01, is almost equal to 0. Then the second output should be 1, which is 0.98, is almost close to 1. Then the third is should also be 1, so it is 0.98, extremely close to 1. And the final should be 0, which is also what we are getting. So this is how we implement back propagation. So that's all for this session. Thanks for watching.